This experiment aims to develop a stable position hold controller by meeting strict error thresholds through a sim-to-real pipeline. By validating in simulation before DJI Teo deployment, we iteratively refine parameters to overcome real-world inaccuracies. Analyzing the drone's internal logic, we see it converts velocity and your commands into motor RPMs. To enable target tracking, we need a pipeline that translates position error feedback into velocity commands to drive rotor actuation. The selected cascaded PID uses its decoupled architecture to separate guidance from plant dynamics. With dual-rate PID and PD loops, it eliminates steady-state error and prevents overshoot during target tracking. These are the control loop parameters, and their impacts on stability and efficiency are mapped for systematic optimization and refined performance of the dual-rate loops. While these initial parameters were chosen at random, they prioritize safety by keeping gains low for baseline stability. Specifically, integral terms are 0 to prevent wind-up and swaying. This configuration met all target reaching and stabilization criteria, providing a solid foundation for further tuning. We use automated GP-based Bayesian optimization to map PID gains to performance, weighting position stabilization higher than yours since yours was more stable. By narrowing search ranges near our successful initial values, we prioritize fine-tuning over broad exploration. Integral turns stay at 0 to prevent wind-up, while a 60 trial cycle evolves from baseline testing to exploitation for final gains. The auto-tuner automates the entire optimization cycle, initializing the flight, recording stabilization metrics, and immediately restarting the next trial. This ensures a rapid, data-driven approach to finding the ideal gain values. The auto-tuner prioritized aggressive target tracking, significantly increasing nearly all proportional gains to eliminate lag and do rigid altitude control while boosting the horizontal inner KD to dampen the resulting oscillations for stability. Evaluating the auto-tuner's output, the shift toward a more aggressive tracking strategy is clearly validated. During the approach phase from point 1 to point 2, the final position error was reduced by nearly 50% compared to the baseline parameters. This improvement extends into the stabilization phase, where both the absolute position error and the position error standard deviation were effectively halved, demonstrating significantly tighter control and higher precision. The return flight from point 2 to point 1 further validates these results. While the tuned configuration consistently yields lower error, it achieves this through significantly higher gains, resulting in more oscillatory velocity commands. Although this leads to a slightly larger initial overshoot, the trade-off is justified by the statistical performance, which shows a dramatic reduction in both mean error and standard deviation. With simulator-tuned controller parameters, the system exhibits significant overshoot in horizontal yaw, forward heading, and excessive climb rates, resulting in instability. This is evidenced by telemetry data showing longer flight paths and setpoint deviations. As the simulator parameters lack the robustness to handle real-world sensor noise, jitter, and ground effects, the proportional gains in the position and velocity loops were reduced, successfully dampening the controller's overreactivity to external disturbances and improving altitude tracking. Furthermore, we doubled the horizontal inner KD gain to increase derivative damping. This provides a critical braking effect that counteracts real-world inertia, eliminating target overshoot and stabilizing heading by filtering out horizontal jitter. Finally, cutting the maximum velocity prevented motor saturation and preserved a critical thrust buffer for real-time corrections. By minimizing aerodynamic drag and sensor blur, we got our most stable and smooth performance to date. To further bridge the gap, we must apply robust margins, increase derivative buffering, and domain randomization to counter real-world noise, non-linearities, and latency. This ensures a stable, generalist system ready for physical deployment.